Our next speaker is Arthur Paul Pedersen, who will speak on the Hahn-Holder. I always keep thinking it should be the Hahn-Holder theorem, so I don't.
Yeah, maybe I can explain why I like just calling it the Hahn-Holder. I'll do that at the end. Maybe someone can guess here. Good evening. It's a pleasure to have an opportunity to speak during this conference in prime time, right? I take this to be so either the diehards are here, and right, and the non-diehards are elsewhere, right? For sure, right? I would like to thank Mel for organizing what has thus far proven, I think, to be a great conference. But admittedly, I can't go through all sessions. It's also in the middle of exam week here at CUNY, but I've been enjoying the sessions that I could catch. This evening, I'll be talking about Hans Hahn's classic embedding theorem for ordered abelian groups. This is the Austrian mathematician around late 19th century, early 20th century into the 30s. And this extension, as the title of my talk suggests, has something to do with Otto Holder, the German mathematician, around contemporary, with lots of important results named after him, right? Or with him, right, as a partner. So I would like to give you some context. I mean, my research interests are cross-disciplinary. It includes mathematics, economics, statistics, psychology, computer science, and philosophy. I went to Carnegie Mellon, an institution well known for sort of an interdisciplinary outlook, and I'm certifiably interdisciplinary. My PhD is in logic, computation, and methodology, right? So which is sort of statistical methodology. So naturally, I approach problems, different kinds of problems, right? Oftentimes it can be conceptual problems, right? And that's my point of telling you this. Namely, it's my attempt to understand and solve a particular problem that led me to doing some interesting mathematics in this case. Well, I do my share of pure problem solving in mathematics and enjoy it very much. In this case, it was a matter of following my nose, right, and trying to find mathematics suitable for addressing the problem, right? So in a case where to ensure that mathematics is in fact not dictating the solution to a problem, right? Which in fact was the problem. I mean, the difficulty. I take these talks, these short talks, 20-minute talks or so, to be advertisements for current research. So to this end, I want to explain why, in addition to the cool math, right, the results I proved have special significance, right, for foundations of probability and decision theory, right, rational decisions, right. Of course, I'll get to the cool business later on, but I do want to motivate it, right. I think that's important to understand, given that that's my sort of intellectual history for this particular project. So enough yakking. So according to theory of personal probability, as Leonard Savage called it, who's a famous statistician you might have heard about, alongside with Dick Manetti, or better known as the theory of subjective probability, right, or subjective probability. And in particular, sort of the orthodox Bayesian canon, right, that you'd see in statistics or hear philosophers talk about or something like that. You're committed to some, highly interdependent network of judgments. That, for example, judgments of probability, utility, and admissibility, choice admissibility, which are subject to standards of internal consistency or coherence, right? And among its chief claims, right, is the thesis that these normative standards require that you are committed to making decisions in conformity with the subjective expected utility hypothesis. So, roughly speaking, this means that at any given time, you're committed to judging a course of action to be acceptable, right? Or to choose from amongst a given set of feasible options, just in case it ranks highest, right? Amongst options that are available to you. Moreover, this is with respect to a single, right, real value probability function. That's what that index P is there. Understood to represent your, in this case, say, probability judgments concerning hypotheses, right? Whatever your question happens to be, and a single real valued utility function, the U, right? Understood to represent your utility judgments concerning action outcomes. So if you were just to take like a pure sort of mathematical probability course, you see random variables all the time, right? You can just imagine that you use the identity function, okay? And that you have linear utility. At varying levels of generality and abstraction, and by somewhat different means, a number of authors, right, here's Wed20, advanced normative accounts of rational judgment and decision making in order to lend some operational significance. Remember, this is the time of operationalism, right, in science, and moreover to justify the theories that were being advanced. So typical accounts expound these coherence or consistency requirements on an agent's judgments and decisions and efforts to ground the subjective expected utility hypothesis. So Wed20, for example, advanced his criterion of coherence, right? Which is just this betting argument you might have heard about, which just prohibits you from adapting attitudes of probability judgments, or more generally estimates for random variables, which commit you to endorsing a decision which is certain to result in a uniform sure loss. So this is a monotonicity requirement. Keep that in mind. We'll come to that later. That is to endorsing the selection of an option in the presence of an alternative course of action, which is better, right? Uniformly in all states, right? No matter what, okay? So that's not good. Although Wed20's account of probability and expectation has been described as sort of like a proto-representation theorem, it can be all described in much the same way that, say, a Savage account, which is just, you know, a binary preference relation and some axioms can. I did this in my lessons. Drawing upon Wed20 and later Ramsey, known for the foundational ideas in probability, and subsequently von Neumann and Morgenstern, themselves known for their seminal theory of utility. Savage, in the center there, Leonard Savage, took a more abstract approach, and he advanced just sort of an axiomatic code of consistency with very rich assumptions on the domain. So the if you were to think of the state space, that's where all the action happens. Whereas with Anscombe and Ullmann, it all happens in the code domain, okay? I can clarify that later on. I have some exercises if you're interested. And they took, basically, Anscombe and Ullmann took sort of like a mixed approach. And what they did is they advanced a set of postulates, much like Savage, but allowed for an intermediary interaction with outcomes that are von Neumann and Morgenstern lotteries with extraneous probabilities, or extraneous meaning just that they're objective probabilities, probabilities which are known, right? And this appeals then to the von Neumann Morgenstern theory, and that allows you to basically calibrate your probabilities and utilities in order to construct subjective expectations. Okay, so again. The shape and direction of these formal developments can be traced back to Hahn-Holder. His ideas, in fact, on the foundations of measurement, right? So he was thinking really deeply about this. in the late 19th century, and then published a paper titled Axioms of Quantity and the Theory of Measurement. And this was later elaborated on ad nauseum by Patrick Supes, Dana Scott, David Krantz, Duncan Luce, and others in hundreds of papers, and famously in their 3 volumes, Foundations of Measurement, which they're good reads, right? You learn a lot if you read them. Well, measurement itself, I mean, has something to do. So measurement is not measure theory, you know, not the bag measure. I'm talking about measurement now, right? It's still an assignment of numbers, right? It has to do with assignment numbers. That's not the entire story. So consider measurement of temperature, or the measurement of mass in physics, where you assign numbers with the goal of preserving certain observed relations, right? So in the case of temperature, the assignment of numbers is to preserve the relation warmer than, right? And similarly for mass, heavier than, okay? Now, suppose you suppose before you is a set of objects, okay? We're going to talk about mass, whose mass you seek to measure, okay? Now, introduce a binary relation, okay, on the set of objects, right? And this is interpreted to express being judged heavier than, okay? Now, successful measurement requires the existence of a real value function, okay, on the set of objects representing the heavier than relation, and moreover preserving a binary relation, okay, on the set of objects corresponding to the combination of objects mass is additive, right? So and so mass, right? Sounds familiar, right? Garbage truck decided to come by. Likewise, in the social sciences, right? When you want to measure preferences, you look for cardinal utilities, which are also additive, right? Or linear, right? Depending on whether you're beginning with a mixture space or some constraints, but it amounts to being additive. And the existence of such representation is assured in all cases by some variant of Hahn-Holder's theorem. Okay, so that's where Hahn-Holder fits in. So basically, everyone appealed, all these, von Neumann, Morgenstern, in some way or other, Savage, Definetti appealed to this basic result that every Archimedean ordered group is order isomorphic to a subgroup of field abilities, okay, under addition. We're going to be returning to this result in a little bit. It's now commonplace for proponents of Bayesianism to complain about the applicability of the normative standards, right? And so and what I want to look at, right, is just to motivate the topic, is the requirement of Archimedeanness, okay? The requirement of Archimedeanness, right, from sort of a logical perspective, right, isn't something that's testable. It's not a testable axiom, okay? It's not something that can be verified, right? You can make this precise if you like. Moreover, it's a technical requirement, right? And certainly there are judgments of probability, right, and judgments of utility, which needn't satisfy the Archimedean requirement, right? For values, utilities, maybe it's easier to think about this, right? Where there are certain things that you're not willing to trade off for others, right? That gives you a lexicographical, right? Which suitably formulated would be in violation of the Archimedean axiom, suitably formulated. Okay. Similarly for probabilities, right? Probabilities, as we'll see, might be required to be non-Archimedean under certain assumptions, right? Or in the assumptions that I have in mind, this is sort of like my modus tollens is your modus ponens, right? Kind of thing. But we'll see, situations where insisting on a dominance principle, like a monotonicity requirement, winds up gets you in a mess. Okay, and then so what I'm going to do now is bring you through an example, right? Just showing you what can happen in sort of a probabilistic theory that everyone here should be very familiar with, I think. But first, I should introduce sort of just a little bit of background, not that challenging. So let omega just be a set of states corresponding to a collection of hypotheses, right, which are individually consistent, mutually exhaustive, right? Mutually exclusive and collectively exhaustive relative to your state of uncertainty, right? The idea here is that the indices sort of are there to just flag to everyone that partitions are divisible, right? This is, even if they're written in small Greek letters, right? And suppose D is a decision problem you face. That is the set of all actions, it's finite in this case, that you judge to be available for you to choose now, okay? Now suppose that for each action Fi, okay, see the red there, I guess I can use that. From the set D, that's listed in the row, in each state Wj, listed in the column, you have identified a unique consequence, and that's Oj, listed right in the center here, to be relevant to evaluating, an action's success. So I'm not assuming that these are numbers, but you can assume there are numbers subsequently. Okay, but relative to your state of certainty, now, right, if you were to implement Fi, right, Oj would result if omega state Wj obtained. Okay, so in the canonical decision problem, it is presumed that there are no moral hazards. So, or that is act state dependent. So my choosing an action doesn't change the state of the world, right? That's a ground rule, right? In the theory of subjective expected utility. You can incorporate these ideas, but that makes life more challenging. And it's assumed that that's all sort of taken care of at the outset. All right, so quickly, I'd like to go over some dominance principles, right? That, some dominance principles, namely simple dominance, uniform simple dominance, and weak dominance. Simple dominance is the requirement that if in each state F is better than G, then F ought to be, the principle of simple dominance listed there in the bottom asserts that if F is better in each state than G is, then F is preferred to G. The principle of uniform simple dominance, that's the requirement that De Finetti's theory satisfies, requires you to add a bonus, okay? And that's the epsilon there, okay? It's a uniform simple dominance, okay? And weak dominance is sometimes better and never worse, okay? So if F is not inferior to G and sometimes better, then F ought to be preferred to G, okay? Now, the heads up here is that simple dominance is violated in the finitely additive theory that you'd be familiar with from densities, right? So let's look at a quick example, right? So suppose you consider a probability function P uniform over the natural numbers and an unknown quantity F, right? So suppose that, you have, you assign same probability, right, to all integers, and the unknown quantity gives you -1 over n, right, for each. Okay. It follows then that the provision, as it calls it, the expectation is 0, right? And this is so by linearity and monotonicity, right? That is the uniform simple dominance requirement. Okay. Just by this simple argument, right? Consider the first n terms. Okay. You'll see that the first n terms must all be 0, right? You repeat this argument, and then you show that P of F must be 0. Okay, that's what's done. So the upshot there is that there are situations where if you want to, so from a subjectivist who's interested in decision making, right, or something like that, or Bayesian who's interested in decision making, would feel sort of obliged to answer, right? And if you're interested in sort of different measures, right, on the natural numbers, ones that don't just assign 0 probability or don't just look at cardinalities, but address things with infinitesimals, perhaps, the way to go is Otto-Holder. And Otto-Holder is famous, or is famous famous for many things, but he's very well known for this result, that every ordered abelian group is order isomorphic to a subgroup of a suitable lexicographically ordered power. Okay, and suitable is just that you have to pay attention to the non-Archimedean, right? And you can look at Archimedean classes, and all that is really interesting. Okay, so let's see. Good. Just let's see. Yep, okay. So this is the result I proved, and that's at the bottom. And then I have additional slides if we get to it. So what I do with the auto with the Hahn result is extend it to fields, right? So let K be a real closed field, and let G be a divisible ordered abelian. Okay, epsilon here is just an indeterminate, right? The Hahn field consists of formal power series of the form expressed there, where the subset F is just well ordered in all the AG are not zero. Okay, it's a support. Okay, well ordered support. And then you endow this field with its natural lexicographic ordering. Okay, described there. Addition is defined pointwise, and multiplication is defined as usual, right? In the sort of power series way. Okay, you can verify that, you can verify then that you get a field. Okay. So what I do, right, is I made an observation that in fact you can go farther with than was done before, which is then to construct in a meaningful way from a Hahn field that is also suitable, right? In order so that every ordered abelian group is order isomorphic to it. Okay, so the quantifiers, I don't get misled by the quantifiers. Let me say it again. Every ordered abelian group is order isomorphic to a subgroup of a suitable Hahn field. Okay, and what's interesting about this is that it's real closed. The Hahn field is real closed because K is real closed and G is divisible. Okay. So it satisfies nice properties, but it doesn't go all the way non-standardized, right? And we know lots about these power series fields. That's a good thing, right? Moreover, if you're interested in measurement, right, as you were Holder, right, and as you were Hans Hahn, he was also interested in measurement. There's an interest in being able to construct the infinitesimal elements, the Archimedean classes, right, that result from, say, your preference or weights, if there could be infinitesimal weights and things like that, right? So this sort of construction, right, actually keeps track of those things. It doesn't just throw a bunch of stuff in there. However, I mean, it's rich enough, right, to have exponentiation, right? It has integer parts. So this is a great place to stop. I got to my theorem. And I do have more slides, and I'm happy to give fancier examples, but I think I motivated my own.
Okay, thank you. So what puzzles me is, what is the connection between what you've been talking about and number theory?
Well, I mean, so the density. So if I try to connect it to the densities bit, right, in the integer parts bit. Right, and so I thought that would be in the background. So if you're unaware about this, there was 1993, there was an article about every real closed field having an integer, right? And so if you're interested then in using these fields to understand integers as we know them, then you can do that with this sort of representation as well by taking suitable. For example, if you're looking at densities, right? This would be a way to investigate densities. So what you call number theory, so it depends on how inclusive one is about number theory, of course, right? But I take it to include probabilistic number theory.
Are there other questions for our speaker?
No, but like I said, let me say that I do. So don't be misled into thinking. Remember, I cautioned at the beginning, or I warned at the beginning that I wanted to give my motivation, right, for coming into this, right. So of course, one could be interested in looking at distribution on the natural and investigate that with this. Okay, this provides a framework.
Okay, thank you. The next talk